we had a dream. And our dream was to build a generalist agent that augments our intelligence and allows us to improve efficiency. So we would like to build an agent that is general enough that allows humans to improve their efficiency in many different tasks. So what are generalist agents really? So today you see many definitions. People have their own opinions about what generalist AI agents are. However, the concept of generalist AI agent has been widely studied in the community for a very long time. I mean, I just said it's a dream since AI has dawned. So what I'm going to try to do in this slide is give you three definitions of people who have defined AI agents so we can have a common ground to start our discussion. So when it comes to Fogel in 1995, the AI agent, generalist AI agent, was defined as an agent that generates adaptive behavior in order to meet goals in environments. So the agent needs to be able to generate behavior in order to meet certain goals. In 1991, so prior to Fogel, the Albus defined the AI agent as a system that can act appropriately in uncertain environments. So we have a system which is acting in an uncertain environment. So the environment is not known a priori. We cannot code all the possible things that could happen in that environment. And now we have that system which is actually acting in that environment, and it needs, to take actions appropriately in order to do well in that environment. So what does appropriately mean in this setup? It means that agents need to take those actions to achieve goals or sub-goals that are defined by the user of that system. In 1998, Nielsen and also Russell and Norvig, I think, mentioned this, if I'm not mistaken. They defined that as a system's ability to reason, represent knowledge, plan, learn, and communicate with other agents. So definitely you can define many other definitions of AI agents, which I am not going to do that here. But from those three definitions stemming back to 1991 in my example, we can conclude the following four things actually. First of all, the idea of having artificial general agents is not new. So it's not a new idea. It, at least in my example, goes back to 1991, and it actually maybe has been the dream since we ever thought about artificial intelligence system. Two, which I think is the more critical point to mention here, AGI agents or artificial general agents are not just large language models. They will need large language models, as a form of prior, as I will describe later. However, they need to go beyond large language models because they need to act in uncertain environments, and they need to plan how to act in these uncertain environments, and maybe they need to communicate with other agents, humans, or the environment itself. Because they need to act in these uncertain environments, we expect those agents to be equipped with sensors to perceive the world, and actuators to act in those environments. And finally, those AGI agents are social, right? They need to talk to other agents, or maybe to humans, or maybe a combination of humans and agents. So from this, we notice that the concept of AGI agents is relatively old. It's not just a large language model, it's more than that. And it also has to, support a multi-agent behavior where the other agent could be a human, or could also be the another, AGI agent itself. So in the history of AI, the problem of defining such types of agents has been well studied, and maybe could be best described under the context of reinforcement learning. So in reinforcement learning, we have an agent, and that agent is working inside an environment. the agent could execute an action in the environment, which we call this action A with the subscript T, to just signify that it's an action A executed at time step T, because the agent is working in time steps in that environment. After applying that action, the environment responds by an observation and a reward. So the observation is just telling the agent where it is in that environment, and the reward is telling the agent how well that action performed in the environment. So the agent is sitting there, let's say I want to go to the door, I'm the agent, and this room is the environment. My current observation, for example, could be what I'm seeing now or my current position. My action could be, okay, go left, go right, go forward, go backward. The next observation could be the new position I'll be in after going forward, for example, if I chose that action. And the reward is, am I getting closer to the door or not? So if I'm getting closer to the door, I'll get a positive signal. If not, I will get a negative signal. Now, of course, the reward can be sparse, the reward is unknown, and so forth. Now, what is my goal as an agent? My goal as an agent is to find a policy pi, which is an action selection rule. So I would like to find an action selection rule pi that will maximize my returns while I'm acting in that environment. So as an agent, I would like to find that action selection rule or policy pi, such that if I execute this policy in my environment, the summation of the rewards, discounted summation of the rewards, will be maximized. So give me that best rule of selecting actions that will maximize my returns in that environment. Now, the action selection rule or the policy typically is conditioned on the observation or maybe the history of observations. And now there are different techniques that you could actually use in order to solve these problems. So I'm sure you've heard about, PPO, TRPO, DQN, and so on. And they're all versions, to kind of solve this form of a problem. Now, maybe originally this problem has been studied under the context of dynamic programming by Richard Bellman, but Rich Sutton was the person with Andrew Bartu to popularize the concept of reinforcement learning in the AI community through their book, which I think I have it here. It's called Reinforcement Learning and Introduction. So this is the book, and I think everybody should read it who's interested in reinforcement learning. It's really a nice book, and it tells us how we could solve these types of problems, going from Q learning, temporal difference learning, to deep learning, and the policy gradients, and so forth. If I'm not mistaken, in the latest version, they do put something about deep learning. So they have a tabular methods, then they have approximate solution methods, and so forth. It's a really nice book. I think we should all read it if we're interested in reinforcement learning. So this method had kind of worked, and maybe the biggest successes you've heard about, from solving the Atari games to beating the world champion in Go, have been kind of applications and additional tricks on top, of course, of this method, where the agent tried to find that policy which will maximize your rewards. And recently, I actually read a very cool paper, which they use also deep reinforcement learning to kind of beat the world champions in a quadcopter game, in a drone racing game, I think, which I think is really awesome. It's super cool. So this method kind of worked, but we have to admit it did not lead to generalist AI agents. So while it worked in certain isolated instances, this is still a pain to get this method general enough to deal with all the engineering tricks you have to do, to deal with the instability of the software and so on. So it really didn't give us the generalist AI agents we dream of, or we had, we wanted to actually kind of develop. So the question is why? What has been missing? Or at least could we take steps, to remedy some of these missing components to get closer to a generalist AI agent? So there are many problems why RL, did not yet generate generalist AI agents, but I'm going to focus on two, which we kind of attempted to resolve in this Pangu Agent paper. The first one is that the solutions are rather too task specific and they require lots of engineering. So we all know, anybody who has worked with reinforcement learning, we all know it's extremely difficult to get a reinforcement learning algorithm to work well on specific tasks. And there's always forms of tricks introduced. Tricks from reward shaping, maybe tricks from using other tasks like in MetaRL, tricks like adding Bayesian priors inside my algorithms, tricks about warm starting my policies, etc. So what is really going on, right, is that to get the reinforcement learning method to work pretty well, we are actually inducing a lot of prior knowledge. We're putting that prior knowledge into the system, and then the agent is taking advantage of that prior knowledge when it's attempting to solve this very sparse reward task. The second problem is kind of that the agent structure and reasoning structure, how it decides to take an action in the environment, is actually prefixed. So for example, if you're dealing with the image-based reinforcement learning problems, right, then what you typically would do is you would maybe have a convolution network-based model. If you're dealing with the textual reinforcement learning, maybe your policy would be based on a large language model and so forth. However, upon fixing this architecture to go from an observation to an action, remember that's the goal of the policy, conditioned on an observation, it needs to choose an action. So this observation to action is kind of prefixed. You just do a forward pass in this network, and then the action, gets spit out at the output of this network. But there is, and now the goal of the agent will become, of course, to find the weights of this network such that you maximize your return. But this is limited in a sense, right? Because the way the agent thinks might require maybe more than one forward pass in this network. It might require using a tool that might help the agent decide about a specific problem. Like, for example, when I am taking an action about something, I might decide, okay, I need to go search the internet. Oh, you know what? If I had a Python interpreter here, that would be very useful. So we want to enable the agent to change its reasoning structure, how it thinks, depending on the task at hand. We would like to be able to give that agent the ability to change its intrinsic way of thinking before deciding on what action to take in a specific environment. More importantly, we want this structure to be flexible. We want to allow the agent, to have a specific structure for this task because this task might benefit from a tool usage, but maybe in that other task, we would like the agent not to have a tool usage, but rather to have a reflection of process with a large language model to think before it decides to take an action. So we would like the reasoning structure of our agent to actually change depending on the task we are interested in. And we don't want to prefix that upfront. So what we've done in this paper was actually try to remedy these two problems. First, instead of having two task-specific priors, we made use of large language model as a good enough general prior. And instead of having a predefined set of structure of reasoning for that agent, we allow the agent to fix its internal structure, depending on the task, via the introduction of what we call intrinsic functions. The LLM prior would allow me to take actions or to have a prior that's general enough because it has been trained on human language data, really. And two, this adaptive intrinsic functions will allow the agent to change its thinking process, its memory, right, before taking a specific action. So in reality, what we have done is we went from the standard reinforcement learning problem definition, which we described above, which was to maximize your return with respect to the policy, into a problem that looks more like this, where you would like to maximize your returns still. However, now your policy is not only conditioned on the observations, but also on a set. We just put this notation vector here to say that this could be nesting of many things, right? But on a set or a nesting of many of those functions mu's. And those functions mu's allow the agent to change its reasoning structure depending on the task we are interested in. And now the goal is to actually maximize the return from the environment with respect to the policy pi and this vector mu. Now, we call those vector mu, or those mu functions, which we call them intrinsic functions. We call them intrinsic functions because they are acting on the agent's memory. So the idea is that those intrinsic functions, they don't necessarily do anything related to the real environment outside. It might record maybe some history and so on, but it's not the one that executes the action in the real environment. All it does is it takes the agent memory, and then it acts on top of the memory of the agent to generate a new memory. So memory at time t, then the mu will act on that memory at time t in ways we design it to. For example, it could be a large language model, it could be a tool, and then it will generate a new memory state for that agent. So that's why we call it intrinsic. It's acting on the intrinsic knowledge of the agent. And the policy pi is now a large language model because we want to have these priors in it. Or could not necessarily be a large language model. It depends on what your task really is. But that policy now, we call it extrinsic function because what it's really doing is that it's taking actions in the real world environment. So we have these two notions. One is intrinsic, that acts on the internal memory state of the agent. And we have the extrinsic function, and that extrinsic function is acting on the external world. And now the goal of the agent is to maximize its return based on both the intrinsic mu, i.e. act internally on the memory, and the extrinsic pi, which is picking actions in the outer world. So I talked a bit about those intrinsic functions, but what do I actually mean? So here I give you a couple of examples of those intrinsic functions. So one intrinsic function is could be, mu1 is a reflection intrinsic function. So this intrinsic function mu1 will take a large language model. It will take the current memory. It will do a certain reflection step, just like a reflect of an LLM. And then it will change the memory state to a new memory state. Or it's this intrinsic function could be a tool usage intrinsic function. So it could take a Python interpreter as input and the memory, and then it can give me some feedback from the tool, which is stored in the memory, and change the state of the memory. So those intrinsic functions are very flexible. They could be practically anything you want that acts on the memory of the agent. They could take different inputs, like here a large language model, an interpreter, and so forth. But maybe the coolest part of those intrinsic functions is that they are composite. So what we could do is we could nest those intrinsic functions in any order we like. So for example, here I show you a composite intrinsic function, which is taking an interpreter first, right? And then passing that to another intrinsic function, which is taking an LLM, like a reflection one. And then the memory will change by, generating thoughts maybe, and also tool feedback. So the idea is that you could actually nest those intrinsic functions in any way you like. And those intrinsic functions could be optimized separately, depending on the task you're interested in. They really constitute the reasoning process of the agent. That's why we call it structured reasoning, because here you can define the structure by which your reasoning process has to take place. And this led us to the development of our Pangu agent. And this is an agent that has the following components. So first, it supports a multi-agent communication. It allows for RL and supervised fine-tuning. Each agent is made of, like, it can have intrinsic functions, like, as we said, a planning intrinsic function, a tool usage, a thinking intrinsic function, and of course, an extrinsic set of functions, which are like act in the environment. It has a working memory, which will store thoughts, trajectories, reflections, messages from the tools, and so on. It has a different prompting templates, and of course, access to many large language models. So we include many tasks in many environments for this agent, like AlfWorld, WebShop, GSM8K. I will talk about them later. So all this is good, but what's really new? So what is really new is that now we think we can help scale reinforcement learning to a generalist perspective, because we support these nesting combinations of intrinsic functions that will allow us to go beyond a think then act architecture. Effectively, or importantly, sorry, we support fine-tuning, both supervised and reinforcement learning, same and cross-domain fine-tuning. So we could do one task for, different environments, like a baby AI AlfWorld environment, or we could do fine-tuning, per specific task. So now our agent, right, it can do what other agents does, but more importantly, right, it actually can go into fine-tuning, both supervised and reinforcement learning, which to our knowledge is the first time a reinforcement learning-based fine-tuning has been shown to scale so far on held out tasks, as I will show later. Right. So, okay, this is all good, right? So I showed you some interesting philosophy, maybe interesting way of thinking, and an implementation. Now, but does this actually work? So in order to test our agent, we included many environments. One of those environments was called AlfWorld, which I'm sure you all may be familiar with. So this is an interactive environment that will align text descriptions with embodied simulations. Like you can say a natural language command, and then that command will get executed into a low-level execution. And it has many household tasks, like, for example, pick up a glass, pick up a pan, and so on. We also made use of Baby AI domain, which was originally designed to include a human-in-the-loop feedback. It includes 19 levels of difficulty. Each is harder than the previous one, and it has grid-like domains. And each domain allows you to create many tasks by randomization. We also had workshop domains, and those domains, they simulate e-commerce shopping scenarios, from 1.18 million real-world products. And the agents here can understand compositional instructions, so they can query, reformulate, and act in web pages. We also had the hot pot Q&A benchmark, which is like a 113K Wikipedia-based questions answering, and many other tasks like standard GSM8K, and also code generation like a human eval and so forth. Now, the first thing what we've done, which I think is actually pretty interesting, is that we noticed that the functions we have, these intrinsic functions we have, they actually map to the real world. They map to the current literature. So the functions that these different nestings of intrinsic functions, right, they actually are a more general case of a lot of prompt engineering techniques that have been done in current literature. So, for example, I show you the disorder nesting in this slide, which we call a first order nesting, where the mu0 is an intrinsic function of just observation, and the mu1 modifies the memory. This form of nesting is actually a special case of our intrinsic function nesting, of our structured reasoning nesting, but it actually corresponds to direct prompting techniques, zero-shot COT, which is like let's think by step by step, or few-shot COT when you give a set of examples. So what is so cool about this formulation, to start with, is that it will allow us with a small number of changes in the code to actually write many of the currently existing prompt engineering techniques as a special case of these intrinsic functions, which then later on we can do much cooler stuff with. But what you can see already is that there's an advantage to this, because now this modularity of those intrinsic functions will allow me to write many special cases. And here we just show you that we run these different techniques on the experiments I mentioned before, from AlphaWell GSM8K to Baby AI. But what is cooler is that I can do a deeper level nesting. So instead of doing this two-level nesting, as I showed you before, if I now, for example, go to a more complex nesting, whereby I have a function selector mu that will decide whether to act and think, and then think itself is another mu and then goes to an act, then actually I have something which we call a react nesting. And that's like a react nesting that has been developed by literature as a very interesting technique. Even if you change this nesting in a different way, you can actually get into a reflect nesting. So instead of thinking here, if you just go from a reflect to an act, then you will get into a reflection sort of nesting. So what I'm trying to show you here is that depending on the order by which you place things and how deep you decide to go in these intrinsic function nestings, you can already recover things that are kind of in literature. So those include in this table, few-shot COT with self-consistency, React, Swift Sage, least to most, and so on. And then again here, we show you that we have run all those on those different tasks. But what is super cool now is that you are able to write these, things in literature as a special case nestings of our structured reasoning or intrinsic function pipeline. Yeah, you might say now, okay, fine, yeah, great, you can do that. But is this just a fancy formulation? Like, why do you go through all this trouble to start with? Okay, well, first of all, there are a set of self-evident improvements. So one is that we can now have, with a small change of code, a unified experimentation protocol across many large language model research and environments. We can also have compositional nesting of any order, and that allows us to have a high modularity design for our agent. Because now you might decide to nest this way versus that way, and that could automatically lead you to a new method you didn't try before in literature. Of course, we try to democratize the LLM research by allowing for many open source LLMs, and we're actually working on trying to open source our agent itself. And most importantly, you can get all those open source models to work really well without needing for any GPT-4 data ingestion. And that is pretty good from an open source research perspective, but more importantly, from a money perspective, because now if you have the right ordering of your intrinsic functions, you are able to show that simple models like Llama 2, 7B can actually work very well, as I will show later. Okay, cool. This is all fine, right? And yeah, okay, it's nice to have a unified experimentation protocol. It's nice to do all that stuff. But it will allow us to do fancy things. And these fancy things are like a new fine-tuning pipeline, which I will describe now. So to describe this, what we could actually do now is we have our agent, right? And we have a set of training tasks, let's say AlphaWorld training tasks in this example. Now, what you could do is you could design a one-order nesting interaction, so one-order structured reasoning interaction with this training task, right? And then, that would be, for example, like a few-shot COT interaction with this task. But with a small change of code, you can go deeper into nestings, and actually you can have a deeper nesting interaction with this environment, for example, using a React, a Reflect, or whatever. And in fact, you can have any other order of interaction that you would like, and any order of these intrinsic functions you would like. Now, what you could do is you can now mix and match, right, the data sets from these different structured reasoning processes. So we can take the data from the first order interaction, we can take the data from the second, third, fifth, 10th, whatever order interaction you wrote. We can use this data to do, for example, supervised fine-tuning, and then we therefore improve our LLM, and then we can repeat this process, right? So the idea is that we can now mix and match different reasoning structures, different intrinsic function orders, in order to get better fine-tuned models that will improve their learning in the next step. We call that bootstrapped supervised fine-tuning. So here are the results, which I think are pretty cool results, because first of all, we tested this on this ELF-World benchmark. Now, please notice that this ELF-World benchmark test is on held out data or held out tasks. So it's like we're assessing the zero-shot generalization of the fine-tuned models on a set of tasks that we don't observe during training. We are using in this example, an open source model, which is this OpenChat V 3.5. And we compare this what I told you about this different order nesting mix and match against direct prompting, few shot COT. What you can see is that after the first step of this repeat loop, we can get to 45% success rate. Second step, 68% success rate. And after 3 steps, to 82% success rate with this OpenChat version 3.5. Remember, those are results in zero-shot, fine-tuning, and they don't use any GPT-4 data. There's no GPT-4 data used here. It's all based on these different structure reasoning processes that will allow me to collect varying degrees of good data that will allow me to combine them and do a mix and match sort of training. So, right, so this seems to work, right? But I mean, 82% is not 100%. Can we try to improve it a little bit? So for that, we designed a reinforcement learning pipeline, which is actually solving, the problem I mentioned to you above about maximize pi and mu. And the idea here is that you can see that this is very similar, to a standard reinforcement learning pipeline, but with the critical difference that now instead of just taking extrinsic function action, based on the policy pi, there is a thinking step or a reasoning step via intrinsic functions that can work with memory, order it, arrange it, compute it, do whatever it wants with it before it allows the extrinsic function to, take an action. So here what we have is this structured reasoning order that I told you about before that will allow us to go from the state of the environment to the action. So this intrinsic function is getting rid of the problem of a prefixed reasoning structure, but allowing the agent to think internally via these intrinsic functions and then act in them. So what we've done is we've done the same experiment I showed you before, on this ELF-World task, right? And so again, we trained on something, zero-shot testing on held out tasks we didn't touch, right? The agent didn't observe during training. And then what you are actually able to see is that once you do this reinforcement learning pipeline, you're actually able to go to 88% in these ELF-World tasks. We also tested on some baby AI tasks, and you can get up to 91% accuracy. What is really critical to show, and I think maybe we should focus on ELF-World more because it's a maybe more complex domain than the baby AI one. Maybe not more complex, but more interesting, let's say, domain than the baby AI one. What you can clearly see is that RL without our intrinsic functions and structured reasoning would completely fail on this problem, right? So it will fail by just leading us to 4% success. However, doing what we did with the intrinsic functions and so forth, we can get up to 88%. I mean, this you can also see in the other baby AI domains where you can always improve, the RL success, like from 87% to 91% or 69 to 77% in these baby AI domains. However, I focused on ELF-World because RL was just generating rubbish, really, 4%. Now, again, this had nothing to do with GPT-4 data ingestion, right? So there was no GPT-4 data ingestion. Now, there's a paper called Agent Tuning, which has actually relied on GPT-4 in order to kind of, fine-tune a llama model as well. And what we can see here is that in the ELF-World domain, right, our model, which is just 7 billion model, could actually get to 88%, while the fine-tuned agent could get to 86%, and just the GPT-4 itself can get to 78%. Now, please note, I would take these results with a grain of salt. I don't think it's a one-to-one comparison between the two, to be honest, because maybe the setup is slightly different. Like, for example, I don't think here they fine-tuned GPT-4. So it's not to say that this method beats GPT-4. I just want to say that our numbers are in the right ballpark and sometimes even better than other numbers reported in the literature. So this idea of structured reasoning can enable RL fine-tuning, right, to do really well, and in, for example, alpha domains. But now what we can even do cooler, right, than what I showed you before, is we can also do a cross-domain model. So the idea is that we can take the AlphaWorld domain experiments or training environments, and we can take the baby AI training environments. Then we can try to build one model and one set of intrinsic functions that actually does well on these two environments. So the idea here is what we do is we can now, take these tasks combined. So they're cross-domain, they're not the same domain. They have different even action spaces, different observation spaces. And then we can train one model and then do a zero-shot test on a combination of the AlphaWorld test tasks and also on the baby AI test tasks. And we do zero-shot test and no additional fine-tuning. And again, these are unseen domains. They're not seen during training. And more importantly, we don't use any GPT-4 data. And then here we can show some of the results. And then what you can see is that this method, the cross-domain method, right, works pretty well. It can take Llama 7 billion from 0% success, right, to 82% success with RLFT, with our RL fine-tuning, and to 40%, of course, with supervised fine-tuning. And please notice that those are all held out tasks. Again, no GPT-4 data ingestion. And now is the story over? Well, not really, because there are still some tasks which we couldn't solve, right? So here what you could see is that the original model, it has like 0% success rate, but the SLFT, supervised learning fine-tuning, or RLFT weren't able to improve it. So there's still some work, to do. However, we can see that based on this structured reasoning in intrinsic order, we can actually improve significantly on many different tasks our performance of the base model, which was Llama 7 billion in this example. So with that, I would like to conclude by saying that we have introduced a nesting ordered structuring for agents. We have showed many good results across different domains in AlphaWorld and in baby AI, both using a single domain and a cross-domain function. And also we have shown that you can have very nice modularity by these compositions of the intrinsic functions. So this is the problem definition we aim to solve. And with that, I would like to thank you. And if you have any questions, please write them in the comments below. And please make sure to read our paper, which is called Pangu Agent, a fine-tunable general agent with structured reasoning. This is the list of amazing authors who have worked on this. And in the paper, we report much more results than I have shown. And if you liked whatever I described and you like whatever we are working on, please do follow me at hboanwar on Twitter or add me on LinkedIn. Thank you so much. We really think that this intrinsic function structured reasoning will help us scale AI. And of course, the next step for us is to actually work on a fully differentiable solver, which is kind of a very important next step to do. And if you are interested in working on those, please don't hesitate to contact us. So thank you. Happy New Year again. And I will see you in a while with some other works related to maybe robotics.